All right, well, I'll begin with a word of prayer. Excuse me. Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to meet together. Just pray that you'd be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. Before I forget, let me give you guys the attendance sheet. There we go. So ask away if you got questions. Yep. 396. Oh, okay, cool. Yeah. So I mentioned that some of the problems involve like a definition that you have to work with, right? So this is one of those. And so in this problem 396, I talk about a little bit about the theory of physics. And so in physics, we talk about a force, right? So for a force in one dimension motion, and let's say, with coordinate x, you could make the coordinate, y if you wanted for vertical motion or something. So let me just give you a brief rundown of a few things from physics. So like Newton's second law says that F is equal to the mass times the acceleration, but we could also write that as like mass times dv dt, right? Or if you like, mass times d squared x dt squared. So this is Newton's second law. All right, and basically you solve that to find out what the motion looks like. Now there's a special kind of force. A special kind of force is called a conservative force. A conservative force. So a conservative force is one for which there exists what's called potential energy. A potential energy function, which for the purposes of problem 396, I'm using a big U for. So F is actually equal to minus du du dx. All right. Now, so this, if it's possible to write your force as the derivative of a position function here, then it's said to be conservative. Now, part of the interest of that is you can also talk about work. Work done by F over, let's say, the interval from x1 to x2 is given by, well, let's think about this. Have you talked about work at all? Have you had some kind of like middle school or high school science course where you talked about work done by a force? Do you remember what the rule was? Force times distance, right. So usually we talk about, like, you got a box or something, you apply a force F naught, it goes a distance d, right? And the work done is just F naught times d. That's force times distance is work done, all right? But the thing is, if this force varies, if it's a variable force, right? If the force is not constant, if it's variable, then the question is if you displace something, some object, some mass m from x1 to x2, you can't just multiply by the force because the force is variable. Which force do you multiply by? F of x1 or F of x2? But what you can say, if you think about it, is that the infinitesimal work done by just a little displacement should be F dx, right? So a little bit of work done is the force times a little dx. That makes sense. And so if we integrate that, we get the total work done. So this is like the next step from like, high school perhaps, or, F is a function of x, all right? So this is the work done by a variable force. What happens if the force is conservative, though? Check this out. So there's also a theorem which says that the work done is equal to the change in kinetic energy. And that's like 1/2 mass times the second velocity squared minus 1/2 mass times the first velocity squared. Kinetic energy is 1/2 mv squared. So you have this, but you also have, for a conservative force, this is equal to the integral from x1 to x2 of minus du dx. But remember last time we talked about the net change theorem? Well, this is like that, right? We're integrating du dx. That gets us the net change in u, but there's a minus. So this gets us minus the change in u. So in the usual notation I use in physics, you've got the following situation. Ke2 minus Ke1 is equal to minus Pe2 minus Pe1. Now I'm using Ke and Pe for kinetic energy and potential energy. This is a notation which Dr. Bodares does not like. He says it's like, it's not, what's the word? It's just out of character. We don't use 2 letters for variable names. I guess he's got a point, right? It's like high school or something. I don't know, but it's near and dear to me. I learned it in community college, so I like this notation. Whatever. But the point is, if the net force is a conservative force, you get this situation that the change in kinetic energy is minus the change in potential energy, which means that you have that the kinetic energy plus the potential energy at the first moment is equal to the kinetic energy plus the potential energy at the second moment. In other words, the total mechanical energy is constant. That's why it's called a conservative force, because if you have a conservative force as your net force, the total energy is conserved. All right? I think one of your homework problems actually has you derive this. Yeah, that's problem 397. You're probably about to ask me about that next, right? Probably, yeah. We'll work through that. 396 is not hard, so you guys help me out. Now, this is just a backdrop. I wanted to show you why these things are interesting, all right? Excuse me, the backdrop is physics. And so like here, part A, for problem 396, we're given that the force is equal to minus kx, all right? Where k is constant. So you guys help me out. We want to say, minus kx equals to minus du dx. So you guys tell me, what does that say? What does that say u of x is equal to? And this is a function of x, not times x, okay? Context here, not multiplication, but functional dependence. Well, integral of kx dx, right? Fair enough. So you're like, well, du is kx dx, right? Yeah. That's not a bad way to think about this. I like that. So this says that du is equal to kx dx, right? Which then if we integrate both sides, we get u is the integral of kx dx, right? What's that? K is a constant. What's that?
Would the first part be k over 2x to 2?
Uh-huh. There you go. I mean, we can add a constant, right, if we want. But if we want the potential energy to be 0 at 0, that would be 0. If we want this, then that makes c equal to 0. So like, there's always ambiguity. There's a freedom here in how you define your potential, but that's it. Just that 1/2 kx squared. This is an important example. Can anybody tell me what it is? What did you say?
Spring energy?
Spring, yes. This is the formula for spring energy. This is the potential energy in spring. And the force at the top is called Hooke's law. This is the formula for the force from a spring. The more you stretch out a spring, the harder it pulls. And x is 0 at the equilibrium position. So if you compress it, then the force pushes back on you, because minus minus is plus. If you stretch it out, then the force is negative, corresponding to the fact that if you stretch a spring out, it tries to pull itself back to the equilibrium position. So that's the formula for a spring, for the force of a spring. That's the potential energy stored in a spring, either if you stretch it out or compress it. Or if you have it at equilibrium, there's 0 potential energy. How about this one? F equals to minus. Now, so if the motion is in the y direction, we're looking for equals to like minus d. So y plays the role x did in the previous one. So we're looking for like du dy. So if I follow you guys' suggestion from last time, this gives us du is like mg dy, so we can integrate both sides, right? And we get what? U equals to what? M and g are just constants here, all right? So the integral of dy is? mgx is the right idea, but change the x to a y, right? mgy. There you go. That is the potential energy. What force is this? F equals minus mg. It's like this one, right? Just gravity. So mass times, so g is like 9.8 meters per second squared. This is the force of gravity. This is potential energy due to gravity. The higher you take the marker, the more potential energy. And it tries to lower its potential energy if it can, like that. Woo! So, whoa! So for part C, the coordinates are, all right? So I'll let you guys do part C, but I'll set it up for you, but I'm not gonna finish it. For part C, you have minus g m1, m2, divided by r squared. So the coordinate here is r, so it's not, you want to have that equal to minus du, dr, so you have to integrate that to find the potential energy in this situation. This formula is actually this is Newton's universal law of gravitation. It says that the force of gravity is inversely proportional to the distance between the masses. That's it. So, did you want me to work out in 397? Yeah, okay. So problem 397. So we have the work is equal to the integral, let's see here, from, let's say, x1 to x2. Well, that's not the right, I haven't defined work correctly, guys. Oopsie. 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 Well, all right. Son of a gun. Well, oh. It's fine. I'll get it eventually, guys. So f of x dx. Golly, how to say this? All right, so if this is the net force, what do we know about it? What did I tell you guys the net, what law does the net force have to satisfy? It has to satisfy Newton's second law. So the force is not just any force, it's force is equal to m times a, right? So F is equal to m dv dt. So we should use that. F is equal to m dv dt. All right. So let's put that in there and see what that does for us. So we're trying to prove the work energy theorem at the moment. That's what problem 397 is about. So, all right. So integral from x1 to x2. If this is the net force, it's equal to m times dv dt dx. All right, I think I need a sneaky trick here. So if you wanted to change this to the integral, say, from t1, no, that's not quite right. Oh man, I think I should have stated this problem in a slightly different way. Oof. I mean, I think we can. I think I can show you guys how to get around it, but there. Oh well. So I basically want to change the integral from dx to like a dt. How would I do that? How would I change the integral from dx to dt? Don't tell the other math professors I did this, all right? But slightly sketchy. But how about this? Okay, so we've got like, you know, I have m dv dt, right? And then how about this? I take my dx, I divide by dt, and I multiply by dt. That seem reasonable? I just divided and multiplied by dt, yeah? And as such, so I divided and multiplied by dt from here, yeah? When I do that, I'm changing the integration from x to t. So I must change the bounds correspondingly to the time we're at x1 and the time we're at x2. So t1 to t2 like that. All right? And then we got to tilt our head and squint. What do we got here? We have the integral from t1 to t2 of m v dv dt. dt. At which point you might go, whoa, hey, maybe we should cancel that dt, huh? Why not? Let's do it. So if I cancel the dt's, I have to change my integration bound again, v1 to v2 of m v dv. But now we can just integrate, right? That's 1/2 mv squared evaluated from v1 to v2, right? Which is 1/2 m v2 squared minus 1/2 m v1 squared. So guys, the way I should have stated this problem maybe is I should have defined work as follows. I should have said that the work is really equal to the integral from time 1 to time 2 of f of x of t times dx dt. Like this is probably the more proper definition of work, but it's also not the definition which is typically given in Calculus 1 either. So, I have no regrets. We're going to leave the problem as it stands. I did, after all, just show you the solution, so you know, there's that. we could have used a trick at the start to like circumvent some of this. Like if you instead use the following trick, so if I like m dv dt, you can rewrite that as m times dx dt times dv dx. See, if I just used that trick at the start, we could have like circumvented like 2 of the steps here and just done that. If you see, if you use this identity, that's v dv dx. So like m times a is also m times v dv dx. This is a trick I use a lot in physics, this particular calculus identity. But anyway, that's the solution to 397. Let me stop talking about this. Enough physics for today. So to calculate the work done by a force in one dimension, we integrate. That was the big story here. There are other applications of integral calculus past this. There are many. You know, we can calculate like arc length. For example, you can calculate the length of an arc. You can calculate the surface area of a surface. You can calculate the force, the hydrostatic force water puts on a dam. See, because that's a complicated question because the pressure for water is different at different depths. Pressure is force per unit area. So to calculate the force that water puts on a dam, you have to like look at horizontal strips of equal depth and integrate the force on each strip to find the total force. Sometimes we cover that. I don't think I have any problems like that in your homework though, so I'm not going to hold you to that, you know. For you guys, the applications are area, volume, and just this physics stuff. Either what's the word? The velocity, acceleration, position problem, right? That's important to us. And you know, in this problem 396, 397. However, I don't expect you to memorize any of these definitions. If a problem like this appeared on the test, I would remind you the definition of work is integrate over x, the force, you know. So I don't really expect you to memorize that. But anyway. So can I race, or do you guys have other questions? Now in physics, this is not like physics 231. Physics 231, it goes past this because in physics 231 we use vectors. So we calculate the work done by a force in 3 dimensions along a path which doesn't have to be one-dimensional. It could be like a curve through space, and we can write down the work for such a situation and work it out. But we need the vector formalism to do that. So, which is part of the reason it's a smart move to take calculus 3 before you take physics 231 if you can. But there's like 2 sides to this. If you take physics 231 before you take calculus 3, it makes calculus 3 easier. If you take calculus 3 before you take physics 231, it makes physics 231 easier. It's like whichever one you take first is going to be your first struggle with vectors, you know. And the second time you circle back to vectors, it gets easier. So it's just nature of the beast, you know. So you guys have questions? No questions? All right. Let's see here. Let's talk about average. So definition, this is another thing that I do actually expect you to know. Average 1 over b minus a integral from a to b f of x dx. This is the average of f on the closed interval from a to b. So example 1. So like, let's see. Let's let f of x equals to x squared. All right, and let's calculate the average. On, oh, I don't know. Let's say 1 to 2. All right. Oh, that's a bad choice. Let's make it 1 to 3. It's a little bit more exciting. There we go. All right, so f average is 1 over 3 minus 1, the integral from 1 to 3 of x squared dx. So what's 3 minus 1 is 2, right? So we've got half. And then integrate, we get a third. So a half times a third is a sixth. 1/6 x to the third power. We got to evaluate from 1 to 3. What do we got? 1/6 of 27 minus 1. So apparently 26 over 6, also known as 13 over 3. So about, what, 4.3333333333. We could be here all day, yeah? What's the meaning of this number geometrically? Do you guys know? Like if I graph this, what's going on? All right, so like here's 1, let's say this is 10, 20, 30. All right, so I'm going from 1 to, I probably should space that out a bit. Space it out. Let me make this, I won't use the same scale. 1, 2, we don't have to have the same scale on x and y, do we? So there we go. 1, 2, 3. So we're starting, this graph here starts at 1, 1, which on my graph is roughly here, and it goes to 327. Wait a minute. Oh, I'm an idiot. What am I doing? Dudes. Come on. All right, so let's make that a 5. And let's make that a 10. Duh. I don't need 30. What am I doing? Good grief. So like this graph goes from what? It goes from 1, 1, 1 to what? 3 what? What's f of 3? 3 squared is? 3 squared is not 6. 9, yeah, 9. So there we go. So we got 3, 9, and 1, 1. And of course it's a parabola, so it goes up like, oops, well I tried. Move my dot there, that's easier. As a general rule of graphing, draw the curve first, add the dot second. Don't try to draw the curve to the dot. Anyway, where is 4.33 in here? So I could make this graph a little bit better if I added the point at 2. What's 2 squared? 2 squared is 4, right? So my picture isn't quite right. So, well, okay, fine. It's good enough. All right, good enough. So 4.33 is something like this, right? So there's y equals to f average, right? So if you think about this, you'd have f average times b minus a, right, is equal to the integral from a to b of f of x dx. So if I was to look at this like, rectangle, like this, that rectangle should have the same area inside it as the curve has under it, since we're dealing with a non-negative function, right? What does that mean? That means that whatever area, if you think about it, right? If I did this graph exactly right, like whatever area is up in region 1, it should be the same as the area that's missing in region 2, right? If I could somehow take this and chop it up into pieces and move it down here, that would be the whole thing. So, Any questions? No? All right, well, let me work another problem then, I guess. You guys don't have questions. So what's happening next week? Monday we got a quiz, right? And you can, of course, ask further questions about homework before the quiz. But they're, these homework questions are lengthy. We do have a test next week. It is, in fact, test 4 on the 25th. That's right. So Monday is quiz 11 and homework discussion. Tuesday is math battle 4. And Wednesday I have reserved for your questions. And then Thursday is test 4. So, yeah. That's the plan. Let's see here. So one more example, I suppose. What do you guys want? Volumes or shell? Volume or area? What's that? Area, all right. Area it is. Let's see here. I got the wrong sheet. Here we go. All right. Let's see here. Problem 378, I'll work that one. Maybe we got time for 2 here. So we got y is equal to the square root of x plus 3, and y is equal to 1/2 x plus 3. We're supposed to find the area bounded by these guys. And I think I have, include a sketch of the area as well as your typical infinitesimal approximating rectangle. All right. So you guys tell me while I'm fixing the camera here, what are we looking at? What's y equals the square root of x plus 3? You should be able to tell me what that is without touching a calculator, without doing anything but thinking. You got to be able to tell me, well, that's the square root function, just shifted 3 units to the what? To the left, right? The funny thing is when we replace x with x plus a, it shifts it a units to the left. You can see this because if you plug in -3, you get 0, right? So like the vertex of the square root function, and of course this is also, you can think of this as half of a sideways parabola. So -3, right? And when you get 0, it's like square root of 3, which is like 1.7. So roughly speaking, this thing looks something kind of sort of like that. So there's your y equals square root of x plus 3 graph. It's half of a parabola that goes sideways. Now, how about 1/2 x plus 3? We should all know that this is a line with slope 1/2, and it has an x-intercept of -3. So it also goes through this point. It's got a slope of 1/2, so it's something like that. I don't know exactly where that point of intersection is yet. I'm pretty sure that this one is at -3. Right? It's obvious that -3 makes both of these have y equal to 0, right? So they do have a common point of intersection at -3. That should be apparent just from basic graphing. Looks to me like vertical. Vertical strip's probably a decent idea here. So let's go with that. So we got like so. The thickness of the strip is dx. So my dA is square root of x plus 3 minus 1/2 of x plus 3 dx. Now, of course, what is not at all obvious yet is what that other point of intersection. Can you guys find it for me? How would you find it? This one right here. How to find that? Set them equal to each other. And in what sense? I mean, you're right, but set the y's equal, right? So, it's not we don't always equate the y. Sometimes we equate x, sometimes you equate x squared. I mean, find something in common to both curves to find the point of intersection, but you're exactly right, equate them. How do we solve that? Uh-oh. Square both sides. I like that. X plus 3 equals to, what happens when you square this?
Would be 1/4 n times, would be x squared plus 6x,
Uh-huh.
and then plus 9.
Yep. You are correct. And of course you said x squared, but I didn't write it. There we go. Multiply by 4 because we hate fractions. We've got 4x plus 12. I mean, I hate fractions. Maybe you don't. We all hate fractions. Okay. That's good. We should always unite over our hatred. It's just a good way to live life. Let's see here. Joking. All right, so 2x. But you know, hatred of evil is actually a healthy thing. We shouldn't discourage that. We should hate what God hates. All right, x squared plus 2x minus 3. So that's, well, I could complete the square, but that would be silly because this is what?
So this is what we mean.
I mean, I could complete the square because, as you know, like, I enjoy completing the square like too much. It's a problem I have. But there's another thing you could do here, known as factoring, right? Just plain old garden variety. I put an x here, I put an x here. You guys give me numbers. Give me the digits. What's that?
What's going on? What side of the factor?
Well, this one, in the blue, in the blue, in the blue.
Would it be x plus 3, x minus 1?
X plus 3, x minus 1. Now, we should have anticipated the x plus 3 because we knew that minus 3 is a solution to this equation, right? Because at the start of all this, we observed that 3 is the point of intersection over here, so that's not surprising. But we just learned that this question mark here is actually at x equals to 1. All right, so now we can find the area. Area integral from minus 3 to 1 of the square root of x plus 3 minus 1/2 x plus 3. Now I have resisted the urge to multiply that out because I want to make a substitution here. I'm going to let u equal to x plus 3. So du is dx. And u of minus 3 is 0. And u of 1 is 4. So making that u substitution, I have the integral from 0 to 4 of the square root of u minus 1/2 u du. And then u integrates to, square root of u integrates to what? 2/3? U to the 3/2 minus 1/4 u squared. You got to evaluate that thing from 0 to 4. So we get 2/3, 4 to the 3/2 minus 1/4 times 4 squared. I think we worked out 4 to the 3/2 the other day. It was 8, wasn't it? 4 to the 3/2 was 8. So we got ourselves a 16 over 3 minus 4. Of course, 4 is also known as 12/3, so we get answer is 4/3. Yay! Excuse me. Ay, ay, ay. Does that make sense? This one here? Is there another particular kind of area problem you'd like me to look at today? No? Yes? We can do like problem 366 is interesting. Find the signed area between y equals sine 2x and oh, here, let's work a reverse problem. We haven't done one of these yet. Let's see here. Suppose we have the integral from 0 to 1 of x to the fourth minus 1 over x. And I better not do that. I better do 1 to 2. All right, this is equal to what? Well, you got yourself x to the fifth over 5 minus, well, plus 1 over x squared, yeah? Oh, I'm a dummy. How do you integrate 1 over x? Come on, guys. Yeah. Minus natural log the absolute value of x, right? Take this thing, value it from 1 to 2, what do we get? We get 32 over 5 minus the natural log of 2 minus 1/5 plus the natural log of 1, which is also known as 0. So what you got here is 31 over 5 minus the natural log of 2, all right? My question is, geometrically, what is this number? What does this number mean? I don't think I asked you guys a question like that in a homework, but oftentimes a question more or less of this form appears on a test, because this is kind of the important thing to understand. Is like, what is the relation between the integration and area? Can you tell me an area? Like, there's a couple different ways to answer this question. All right. So I think there's two natural ways to answer this question. The one is just to say, well, that's the area under the curve y equals x to the fourth minus 1 over x from what? From 1 to 2, right? That's one answer that's possible here, right? You can just say, well, answer number 1. So here's my question. Answer 1 just might be, if you look at y equals x to the fourth minus 1 over x, this is area. Signed area, rather. You know, under y equals f of x. This is f of x. Under y equals f of x for 1 less than or equal to x less than or equal to 2. That's one way you could say it, right? Answer 2, though, I think might be more interesting, which is it's the area bounded between which two curves? It's the area bounded between, let's say, 4 curves. Blank, 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 and blank. If I wanted to force the issue on a test, I might write it this way. Fill in these 4 blanks. The 4 blanks would be this. I'll do the easy ones. X equals 1. X equals to 2, right? So if you think about this geometrically, we've got 1, we've got 2, we've got x to the fourth, it goes like this. X reciprocal goes like this. Right? 1 over x starts at 1, it drops to 1/2. Y equals x to the fourth starts at 1. They both start at 1, 1, right? But this one goes up to 2/16. The other one goes down to 2/1/2. But this area right here, that's the meaning of this number. It's the area bounded by these two curves. So they fill in my other blanks. Y equals x to the fourth, and y equals 1 over x. So this is the meaning of this calculation. It tells me the area bounded between those two curves, given those limitations on x. Now, I see now that I could have done what? I could have made it just 3 blanks. Yeah? Because we didn't really need the x equals 1, did we? Or did we? Oh. No, we do. We don't, because of the context here, the integration. See, the integration forces the x equals 1 and x equals 2 on you. Anyway, so enough about that. Hey, have a good weekend, you guys. The final exam is cumulative, and it's pretty much just on what we've talked about up to today, and whatever appears on, test 4 and quiz 4 and quiz 11, math battle 4. So like the stuff we have in the assignments next week is the end of the material. Okay. Yep.